In this video, we are going to look at the problem of multiplying two large integers. Suppose that you are given two integers, let's call them a and b, both of which are n bits long. How fast can you multiply them? So we can write a as a sequence of n bits, and we can write b as a sequence of n bits as well. A is written as A1, A2, and so on till AN. B is written as B1, B2, and so on till Bn. Each AI or Bi is a single bit, either a 0 or a 1. Now, if the number of bits, that is n, is small enough, let's say it's smaller than 16, then you can straight away multiply these two numbers by using the built-in multiplication operation in the programming language that you use. For example, in some programming languages, you could have an integer data type that is 16 bits or 32-bit long. And if the number of bits in your two integers is less than 16 or less than 32, or whatever the upper limit is for that language, you could use the built-in multiplication operation to multiply these two numbers. And that's going to take a constant amount of time. But we are assuming here that the value of n could become arbitrarily large. You could have two numbers, both of which are say 2000 bits long. Now that would exceed the capacity of the integer data types in the standard programming languages. So how would we multiply these two numbers under that circumstance? So clearly this approach is not going to work. We can't just create a simple function called multiply where we take in these two numbers and just return a multiplied with b, because this multiplication operation may not work for arbitrarily large integers. Since a and b may be too large to fit into standard data types like int and so on, we need a more sophisticated algorithm to multiply the two integers. A brute force way of multiplying a and b would be to use the standard paper and pencil algorithm that you would have learned in school, where you take the two integers, line them up, the second one below the first, and then you take every bit of the second integer and multiply it with all the bits of the first integer. So for example, we could take b sub n here, this bit, and multiply it with all the bits of a and write down the result in n bits. Then we take the second last bit of b, multiply it with all the bits of a, and write down the result shifted to the left by one position. Then we take the third last bit of b and multiply it with all the bits of a. Again, write down the result shifted to the left by two positions. And so on. We continue this until we have multiplied b1 with all of these n bits. And then we just add the result. We just add all these n strings column by column to get the final result. If these two numbers are n bits long, it's possible that the final result could be approximately 2n bits long. What would be the time complexity of this brute force algorithm? Since we are taking every bit of b and multiplying it with all n bits of a, To calculate each of these strings is going to take time proportional to n, because to multiply a bit of b with all the bits of a and to write down the result here is going to take time proportional to n. Now either b sub n could be 0 or it could be 1. If it's 0, we just write down a string of n zeros. If it's 1, we just copy a and write it down in place of uh, along this line. So this is not a complicated multiplication, but still writing down the result, whether it's 0 or whether it's just a copied over here, is going to take time proportional to n. And that applies to every single string over here. Now since there are n bits in B and each line here corresponds to one of the bits, we will be in effect doing n square multiplications in total, or we'll be using time that is proportional to n square, because if the first string takes time proportional to n to be written down, the second string takes time proportional to n to be written down, and so on. There are n strings here, and so the total time taken to write down all of them will be n times this some constant multiple of n, which would be cn square. So there are n such strings or numbers here, and generating each of them takes time proportional to n. And so the total amount of time needed to write down all these strings is proportional to n square. And likewise, when we add up all these strings column by column, we will have about 2n columns in the worst case, and adding up each column could take time proportional to n again, because we are adding n bits. Since we are adding n bits and we are adding over about 2n positions, the total time spent in adding up all these numbers to generate the final result will be proportional to n square. So this brute force algorithm runs in time proportional to n square. Could we do better than this? Well, let's try using a divide and conquer strategy to develop an algorithm. Here are the numbers a and b again. Both are n bits long, and I have denoted a sub l here as the left half of a. So a sub l is the first n by 2 bits of a, and a sub r is the right half of a. Similarly, b sub l is the left half of b, or the first n by 2 bits of b, and b sub r are the remaining n by 2 bits of b, or the right half of b in the binary representation. Now, in trying to develop a divide and conquer algorithm, let's assume that we already know how to multiply two numbers that are n by 2 bits long. Let's say we have a friend who knows how to solve the problem when the two integers are n by 2 bits long. Now we want to divide the problem that we are given into smaller pieces such that we can just hand over those smaller pieces to our friend to solve, and then once we get the result from him, we can combine the results to generate the solution to the original problem. Now that is why we have divided a and b into two halves over here. So let's see how we can divide this problem into sub-problems. If a is divided into these two halves, a sub l and a sub r, then a can be written as 2 to the power n by 2 multiplied by a sub l plus a sub r. And b can be written as 2 to the power n by 2 multiplied by b sub l plus B sub r. That is, in order to generate A or B, we can take the first n by 2 bits, multiply them by 2 to the power n by 2, which is equivalent to shifting them to the left by n by 2 positions and filling in the remaining positions with zeros. And then we add the right half of A to that shifted string. So let's take an example. Suppose this is an 8-bit number. We can write this as the left half multiplied by 2 to the power 4 plus the right half, which is 1001. Of course, this is the binary representation, and when I say 2 to the power 4, I'm using a decimal notation here. But the idea here is that we can take the left half and shift it to the left by 4 bits. So that will make it 1101 and 4 bits, 4 zeros to the right of it. This is what this means. It means you take A sub L and you append n by 2 zeros to the right. And then you add to this the right half. The right half here is 1001. And by adding these two, we regenerate the original number. So instead of thinking that there are two numbers given to you, think of there being 4 numbers. The first number is the number corresponding to A sub L. The second number is the number corresponding to A sub R. The third number is the number corresponding to B sub L. The fourth number is the number corresponding to B sub R. Now, using these 4 numbers, you can calculate how to generate the product A times B. Because if A and B are given by these two expressions, then their product, if you multiply these two expressions term by term, this term multiplied by this term will yield A sub L multiplied by B sub L multiplied by 2 to the power n. That's the first term. The second term will be A sub L multiplied by B sub R multiplied by 2 to the power n by 2. So if we take the first term here and multiply it with the second term here, we'll get A sub L B sub R times 2 to the power n by 2. Similarly, if we take the second term here and multiply it with the first term here, we'll get A sub R multiplied by B sub L, the whole thing multiplied with 2 to the power n by 2. So we can take 2 to the power n by 2 common, and we'll be left with A sub L times B sub R plus A sub R multiplied by B sub L inside the brackets. And if we multiply the second terms of both expressions, we'll get A sub R multiplied by B sub R. So this is the expression for the product of A and B. So if you're given these 4 numbers, A sub L, A sub R, B sub L and B sub R, all 4 of which are n by 2 bits long, you can compute the product of A and B by doing these computations. So you take A sub L, multiply it with B sub L, shift the result to the left by n bits. You multiply A sub L with B sub R, you multiply A sub R with B sub L, you add the two numbers and then take the result and shift it to the left by n by 2 bits. And you also compute what the product of these two numbers is, A sub R and B sub R. And then you add these 3 resulting numbers. This is what A times B would be. Now let's assume here that we would compute these 4 products by handing, so these 4 are the subproblems where we are multiplying two numbers of size n by 2, and we're going to hand over these subproblems to our friend who knows how to solve them. Or in other words, we'll be making recursive calls to subproblems of smaller size, of half the size as the original problem. So if t of n is the amount of time it takes to multiply two n-bit numbers, t of n by 2 would be the time needed to multiply two numbers each n by 2 bits long. Since there are four such products we need to compute, we would need to make four recursive calls on subproblems of half the size. So the amount of time needed for these four multiplications would be 4 times t of n by 2. And then the time taken to combine uh, these four products into the overall result would be linear in n or proportional to n, because shifting this result to the left by n bits is just going to take time proportional to n. Computing the sum of these two numbers, each of which is say about n bits long, because you're multiplying an n by 2 bit number with an n by 2 bit number, so the result would be approximately n bits long. So the amount of time to add two n bit numbers would also be proportional to n. And then shifting the result to the left by n by 2 bits would take time proportional to n, because you would just need to add n by 2 zeros to the right. And likewise, computing this would take time t of n by 2, and then adding these three resulting numbers would also take time proportional to n, because these numbers themselves are of length proportional to n. So adding three numbers, each of which has a length proportional to n, would take time proportional to n. So we can write the total time required to combine these terms into the overall result as c times n. So in this divide and conquer strategy, we are going to end up with a running time t of n that's given by 4 times t of n by 2 plus c times n. We know how to solve recurrences of this type. We can use the master theorem here. A is 4, b is 2, f of n is c times n. So if we compute n to the power log base b of a, we will get n to the power log base 2 of 4, which is n square. And if we compare n square with f of n, we see that n square is polynomially larger than f of n. And so we are in case 1 of master theorem. And by case 1 of master theorem, t of n will be given by theta of n to the power log base b of a. So t of n is theta of n square. Now we can immediately notice here that the running time of this divide and conquer algorithm is no better than the running time of the brute force paper and pencil algorithm that we just saw a few minutes ago. This means that using the divide and conquer strategy here did not help us improve the efficiency of the algorithm. We got an algorithm with the same asymptotic time complexity as the brute force algorithm. So it's not necessary that by using a divide and conquer strategy, you will necessarily get an algorithm that is optimal or that is faster than just a brute force algorithm. In some cases, that may be true, but we are not guaranteed to end up with optimal algorithms just because we are using the divide and conquer strategy. So let's see if we can do better than theta of n square by modifying this divide and conquer strategy, we will again use we will again develop a divide and conquer algorithm, but it's going to be slightly different from this relatively straightforward algorithm.